It is time for the last lesson in Chapter 12, CTM students. Welcome to the lesson about the binomial probability formula. It can be found on the pages listed there. We're going to talk about the formula mostly today, and you should know what probability distribution is, probability distribution, by the end of this lesson too. So let's get into a couple of definitions. First of all, more of a definition down here of the binomial probability formula. I'm trying to talk too fast. But to use this formula, there are some requirements. So these are the requirements for using the binomial probability formula. Three things. One, this has to be true. There are n, some number, there are n repeated independent trials. They must be independent. Doesn't work otherwise. So they have to be independent trials. So something like having things with replacement. So you put stuff back in there, you have the same probability then the next time around. Things that are dependent or without replacement, things of that nature, this doesn't work for that. So it only works for independent trials. Second thing that has to be true, a second requirement, each trial has, and when you see that prefix by, you should think of two things. So like a bicycle, something like that, two wheels. Each trial has two possible outcomes. So each trial has two possible outcomes. We're going to call those outcomes success and failure. And a third thing that has to be true for each trial, the probability of success and failure remains the same. So it has to remain the same throughout. Remains the same. And then here it is. Here's the big guy for this lesson, the binomial probability formula. So up here we're saying we can use this now because these three things were true. These three requirements held fast. They worked. They're good to go. So this is what the binomial probability formula is. Probability of obtaining exactly x successes, not n, x successes. I'm going to use the letter n for something else. So x successes, p of x, capital P of x, probability of x successes in n independent trials. There's our n. So in n independent trials is given by, and here's the most important thing to remember from this lesson, the formula itself. So P of x, probability of x, equals, you have n choosing x times lowercase p to the x power times lowercase q to the n minus x power. And at first, you might look at that and say, what on earth is that? That looks like way too much. It's not bad, okay? Just wait for it, alright? So what do these things stand for? We haven't even defined what lowercase p and lowercase q stand for, so let's do that right here, where p, lowercase p, is the probability of success on a single trial. So lowercase p is going to be success, and lowercase q is going to be failure. So in q is the probability of failure on a single trial. And yes, this looks kind of daunting at first. I would agree if you're thinking that right now. But once we start plugging in numbers and realize, oh, this is what n is, this is what x is, this is what p and q are, it's actually pretty easy. So let's get into just the part where I want you to listen for a little bit and make a connection with something else, a famous guy, Pascal, sorry. I think his first name was Blaise, if I remember right, Blaise Pascal. He did a lot of work with mathematics, and he came up with this triangle, or we at least attribute this triangle to him. But I want to show you a cool connection. Right now, just listen, just watch. I'll write this in green to remind you that this is not a normal thing we're doing here, writing down. Just want you to watch this and see how these connections are made. So this Pascal's triangle, you'll notice as you go down that as you kind of put the two together, they're going to add to that next number. Here, here, here. These will add to these, and so on. So that pattern continues all the way down. But this is actually 0, choose 0. 0, C, 0. If you go down to here, this is row 4, and let's say you picked this one. This is actually 4, choose 1. Row 4, this is the 4th row, and so 4, picking 1, 4 choose 1 equals 4. If you picked, well, let's pick a more obscure one maybe, so this one would be, this is row 7, so this is where 7, choose, and this would be choosing none, 1, 2, 3, 4, and 5. So this would be 7, choose 5. If you put that into a calculator, or you work it out the long way, remember it's just, we have 7 factorial over 7 minus 5 factorial times r factorial. So if you did this, you would get 7 factorial over 2 factorial times 5 factorial, which is 7 times 6, oops, I meant to write 5 there. Again, we're just listening to this part here, but yuck, that is awful looking. Okay. So it's 5 factorial. So this is the same as 7 times 6 times 5 factorial over 2 factorial times 5 factorial. These guys cancel. You'd be left with 7 times 6 over 2 times 1, which would be 42 over 2, which would be 21. Fancy that. Look at that. So 21, that's right there. If you pick this one, this would be, this is 10, choose, this would be 0, 1, 2, 3, 4, and 5. So you can use Pascal's triangle. If you didn't have a calculator that could do this, you could recreate Pascal's triangle and figure out what 10, choose, 5 is based on that. You just go 1, 1, 1, start with that, and then just start going from there. Each side here, each side here, as you go down the triangle, it all starts with 1 here and 1 here. And then the next ones are just sums of those. So cool little connection. Just wanted to point that out, and we'll do a couple examples now to demonstrate the binomial distribution formula. And so that NCX, you could use this table. That's why I wanted to point it out. There's connections to math all over the place. But here's the problem to start. Example 1. A bag contains a bronze, silver, gold, and what these are, this is platinum actually. A lot of people would say platinum is more valuable than gold. So platinum metals generally are even considered to be higher than gold metals. So platinum, but these are going to be coins instead, so platinum coins. These are real platinum coins that the U.S. Mint has actually made. I don't know how much they're worth, but they're platinum coins. And so we're going to pretend that we're going to pick 4 coins. So we're going to say, hey, you got 4 platinum coins in a row, but 4 platinum coins, 4 coins are to be, we're not saying 4 platinum coins yet, just 4 coins. 4 coins are to be selected with replacement. So we don't actually have 4 platinum coins in this bag, we just have 1 of each kind. 4 coins are to be selected with replacement. Very important there that it's with replacement, otherwise we could not use the binomial probability formula. So let's do this. Find the probability that, then part A, no platinum coins are selected. So let's draw a little bag up here. Let's do that. You can draw your bag, I guess, however you want to. But we're going to have in here 4 different coins. One's platinum, P for platinum, G for gold, S for silver, and B for bronze. I'll refer back to that just to help us think about this. So if you take out the platinum coin, there's a 1 out of 4 chance of that happening, but we're saying with replacement, so we put it back. So each time the probability stays the same. If you took it out, didn't replace it, you would have a 0 out of 3 probability for drawing a platinum coin the next time. So with replacement, keeps all the probabilities the same. I want you to circle this, use a different color at this point. So different color time. Pause if you need to, and make this note, because we need to have these 3 requirements being fulfilled before we can use this. So there's going to be n repeated independent trials. There's going to be 4 independent trials. We're going to pick 4 coins out of here. Each trial has 2 possible outcomes, success and failure. So our success would be pulling a platinum coin for what we're going to be doing. Failure is not getting a platinum coin. And for each trial, probability of success and failure remains the same. That's what we're doing here with step 3. That's why we have to say with replacement, otherwise it changes the probability. So this makes the trials independent and the probabilities stay the same for each trial. Okay, so that's a little side note. I think important to note that. So that fulfills our 3 steps there. That fulfills at least step 3. The other 2 were fulfilled by what else we have in here. So no platinum coins are selected. So let's figure this out here. The probability of success. We're trying to use this formula back here. We're trying to use the binomial probability for this. So we need the probability of success and the probability of failure represented by P and Q, lowercase p, lowercase q. We also need to know what x is and what n is. So there's 4 things to know. Once we know those 4 things, we can just plug them into this formula. So let's figure out what those 4 things are. So this we represent with lowercase p, just with this kind of problem, binomial probability problem. And so that is 1 out of 4. We have to determine that. That would be success, pulling the platinum coin out of there. So let's circle that. That's pretty important. That's something we're going to use as we solve this problem. Probability of failure is going to represent, or be represented by Q. And so there are 3 out of 4 coins that would be a failure for us if we're trying to get platinum. So Q is going to be 3 out of 4 instead of 1 out of 4. Notice these 2 added together add up to 1 like they should. So there's just 2 things that can happen, success or failure. And we're saying here that n is equal to, well, there's 4 coins that we're going to pull. So n is going to equal 4. And x, in this case, no platinum coins. So our x for this problem becomes x equals 0. Let's make some side notes off to the side for these 2. So we're going to be picking 4 coins. So we have 4 trials. Okay, so write that off to the side there. And then x equals 0. We're saying no platinum coins. Let's underline no and say picking 0 platinum coins. Okay, so we're trying to pick none. That's why x equals 0. So with all that said, now it's real easy. Now we just have to plug it into the formula correctly. So our formula is, this is the general formula. I'm just going to write this down in the general way one more time, and then from there we'll just be plugging the numbers in immediately in the following examples. So this was the general formula again. So n choose x, and then p to the x power, and q to the n minus x power. And so our x is 0. We're trying to pick 0. So the probability of picking 0 platinum coins, and n is 4. I'm just taking my numbers right here and plugging them in. So C, n is 0. So choosing 0 out of 4. And then P is going to be 1/4, so 1/4 to the x power to the 0 power times 3/4 to the 4 minus 0 power. That's an ugly minus sign, there we go. So this, after we do this one, I'll show you the other way you could do this and show you why this is such a beautiful formula, why it's so helpful with problems like this. So for choose 0, I'm just going to say I use my calculator with these things. We can do that here too. You need to know how to do these by hand, but you can use your calculator when I tell you it's okay. And right now I'm telling you it's okay. Or you can use your calculator to do that. So I could actually go back here too and figure it out from here. For choose 0, anything choose 0. There's only one way to choose 0 from a group of whatever number of things. So that's 1 times, then 1/4 to the 0 power. Let's leave that like that for a moment. 1/4 to the 0 power is, we'll just leave it like that for the time being. And then we'll have 3/4 to the 4th power, 4 minus 0. This becomes, still got your 1. Anything to the 0 power except for 0 is going to be 1. That's just a rule of exponents that we need to know to do problems like this. And then here you have 3/4 to the 4th power. That's 3 to the 4th power on top times 4 to the 4th power on the bottom. That would be 81 over 256. So if we multiply 1 times 1, that's 1, and 1 times this is just that number still. So your final answer for something like this, 81 out of 256. And so it's nearing 1/3, not quite 1/3. And I would say that there's a pretty good chance of that happening because you've got 3 out of 4 each time, but to say that it never happens out of 4 picks, that's going to be a little tougher than just a plain old 3 out of 4. So about 30-ish% looks like there. Seems like a reasonable answer. And so I had promised to talk about a different way. I'm going to write this in green. Reminder there, green stuff. Don't write it down. I just want you to listen. So another way you could have thought about this was to do a tree diagram. So just listen right now. I don't want you to draw this down. But you could have had branching off from here, 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 and here. You could have 4 picks for that first one. So you could have said platinum, gold, silver, bronze, order. Doesn't really matter. And then from each one of those, this would be your second pick. You could have platinum, silver, gold, bronze. You'd have 4 branches off of each one of these. You'd have 4 branches off of each one of these. And then off of each one of these, you'd have 4 more branches. 4 more branches. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and then that would be your first, that would be your second. This would be your third pick. And then this would be your 4th pick. So you'd have to do another one of these. And so you'd have 4 times 4 times 4 times 4 more. That's 256. And your sample space would contain 256 possibilities. And if you didn't use this binomial probability formula, this is another way you can think of this. But I don't think you want to figure out the sample space and put all 256 possibilities down and figure out how many of those exactly contain no platinum coins, which ends up being 81. So you'd end up picking or looking at 81 out of 256. And then if you had to do this for 1 coin, which is what we're about to do, then you'd have to look how many have exactly 1 coin and do that. That's why this is so nice. It just allows us not to do this, and not to have to do this, or to rely on computers necessarily to figure it out for us. So we don't have to calculate the whole sample space to be able to do problems like this. So we'll continue this problem here, part B though. So now start writing again. That was just a listen. Oh wow, that's nice. I don't have to do that. Yay. Okay. So exactly 1 coin, 1 platinum coin is selected. Exactly 1 platinum coin is selected. So what's the chance of that happening? I'm not going to rewrite everything here, but think about it. These two are still the same, 1/4 and 3/4. Your n is still going to be 4, but now we're saying x equals 1, picking 1 platinum coin instead of none. So that's the only thing that's going to change. And so let's just plug it right into the equation without writing the general formula first now. So we'll have too big of a 4, it's got to be a small 4, sorry. So 4 1 times, this is still 1/4 for my success, to the first power now, that's to the x power, this is x right here, and then 3/4, still my q, still my probability of failure, to the 4 minus 1 power, to the n minus x power. Plug that into a calculator, or just think about it, there's only one way to pick all 4. I mean, that's not what I meant to say. There's only 4 different things you can pick from the group of 4. So this becomes 4. You can use your calculator to do that as well. Then 1/4 to the first, 3/4 to the third power this time. This becomes 4. This is just 1/4. And this is just going to be 3 times 3 times 3, 27, over 4 times 4 times 4, 64, right there. I'm going to, you could write this over 1. You could say, oh, 4 times 1/4 is 1, do that. I'm going to just multiply it all the way through first on this, and I'll show you why, or we'll see why that is at the very end. But you could reduce right now if you wanted to. Okay, you could do that too, so don't feel like you couldn't do that. This, though, 4, I can write this as 4 over 1. I'll write that, have you write that in too. So that's 4 over 1. This would be 4 times 27 times 1 on the top, and 4 times 27, that's 108. Here, 4 times 64, 256 again. And so you could reduce this down to 27 over 64. That should also make sense based on the fact that 4 times 1/4 is just 1. So 1 times 27 over 64 becomes 27 over 64 still. Now let's say you are picking exactly 2. Exactly 2 platinum coins are selected. And with this first example, we're going to go through all the different possibilities, 0, 1, 2, 3, and 4. So we got a couple more parts, but now that we're getting the hang of this, I think we can do this a little bit more expediently. So 4 choose 2, then 1/4 squared, 3/4 to the 4 minus 2 now. So just plugging in the numbers, 4 choose 2 is 4. No, it isn't. It is 6, sorry. 4 choose 2 is 6. 1/4 to the second power, we'll simplify that in a moment. 3/4 to the 4 minus 2 is the same as 3/4 to the second power. So this would be 6. You can make it a fraction. Let's write 6 over 1. This would be 1/16. And this would be 9 over 16. Now again, we could reduce the 6 and a 16 right now if we wanted to. I'm going to not reduce until later for a reason yet to be revealed. But these two could be divided by 2 and 2. You could reduce that to 27 over 128. And there's a trend going on here. It seems to be getting less and less. The probability seems to be getting lower and lower with each one. Maybe not here, but now it's going to start to get lower. So 27 over 64, that was actually a little better than none picked. But then it's going to keep getting lower in here now. So the probability of getting exactly 3, that's going to be pretty hard to do. Exactly 4 is going to be really hard to do. And so those probabilities should be pretty small. Page after current, there we go. We're going to need one more page here for this one. So exactly 3 platinum coins selected. So getting more probability practice with this right here, getting more practice with the probability formula, binomial probability formula. We got 4 choose 3 times 1/4 now to the third power, and then 3/4 to the 4 minus 3 power. I'm thinking of my next step already. 4 choose 3. There are 4 ways to do that. This would be 1/4 to the third still. This would be 3/4 to the first now. And so this becomes 4. You could write that as 4 over 1 if you felt like it. I'll do that here. This would be 1 over 64. This would be 27. I'm sorry. Man, no it wouldn't. This is to the first power, Mr. Wagner. Thank you. Okay, thanks for that reminder. This would just be 3/4. And so here I have 4 times 1 times 3. That is 12. 1 times 64 times 4, 256. Could you have reduced right here the 4 and the 4, or the 4 and the 64? Either way, yeah, could have done that. But I'm going to leave it like that as a helpful little guide for something later. We're still yet to reveal it. I know the tension is mounting. It's just unbearable. You just want to know, why are we leaving it like this? Why aren't we reducing yet? Patience. Patience is a virtue. Exactly 4 platinum coins selected. So now, what should be the most difficult, most challenging to do, probability of 4. Let's see if that jives with our answer. It should be the lowest probability of any of these. So 4, choose 4. There's only going to be one way to pick all 4 from a group of 4. This would be 1/4 to the 4th power. This would be 3/4 to the 4 minus 4 power. This is going to be one way to do that. This is 1/4 to the 4th and 3/4 to the 0 power. So this becomes 1, it's a 4 right there, sorry, times, you could write it as 1/1 if we wanted to, 1, and this would be 256 on the bottom there. 3/4 to the 0 power, that's just 1. So you still have 1 times 1 times 1/256. That's 1/256. And so if you look at these, this is why I did this. 1 plus 12, okay, that's 13. 13 plus 54, that's 67. 67 plus 108, that is 175. And 175 plus 81, that is 256. And so if you add the sum, redundant, Mr. Wagner, hello, okay, if you take the sum means to add, so if you take the sum of all 5 of these are all 5 possibilities. You could pick 0, 1, 2, 3, or 4. If you take the sum of all those, they all should add up to 1, because the chance of anything happening in the end, these are the only 5 different things that could happen. You could pick 0, 1, 2, 3, or 4. If you add them all up, they better add up to 1, otherwise you did something wrong. So we're not going to do, each time you're not going to pick, we're not going to find the probability of, if there was like 8 things that could happen, you're not going to find the probability of all 8 necessarily and then add them all together. But that is a way you could check your answer. So off to the side, in a different color for this one, I want you to write a little note here. So a note about example 1. So notice, different color for this please, notice in example 1 that we calculated the probabilities for all options for selecting platinum coins meaning that the sum of all probabilities, let's say all here, so all probabilities should be, and we did check it, so I'll say and is 1. And so we checked that out. A nice way to check our answer on this one to know that we got it right. So I want to do one more example, just one. There's 4 more in the book if you want to check those out. They have some really good explanations of why the probability, or why the binomial probability formula works. I feel like I've tried the best and feel like I've done a pretty good job explaining why it works and why it's nicer to use than a tree diagram, for sure. So, as always, though, let me know if you didn't understand something, if something didn't make sense in what we were talking about. Talk to me in class if you're one of my students. So suppose that, this is example 2, suppose that the probability that a person selected at random has a PhD is 1.27%. So I actually did look at some census data from the US Census data, and it was supposedly a little bit above 1%, so I'm just going to go with 1.27%. So not a very good chance. Roughly a little over 1 in 100 people would have a PhD, so hard to get those. Got to be not only pretty smart, but you got to have a really strong work ethic too to get a PhD, I would say. You just got to keep doing more and more and more school. So find the probability that we're going to do 3 parts to this one. So part A, exactly 2 people of 10 selected at random has a PhD. And so I have my bachelor's degree right now. I'm thinking of going for some more schooling to try to go for the master's while I continue to teach. But I've heard things about grad school. If you go beyond your master's degree and go to grad school, I've heard things like this are true. So all-day napping, how it's like kindergarten, it's okay. Constant adult supervision. There's constantly going to be these adults being like, hey, do you have your thesis done yet? Or how is this coming? How is that coming? You get cookies for lunch. Copy and pasting. Bad. That's bad. That means they're plagiarizing. Not good there. No, there are no grades. I think some grad schools are like that, and you just like your thesis. That's the big thing. And did you do your thesis? Did you pass or fail? And crying for your mommy is normal because there's so much work involved with a PhD. So if you're going to go for a PhD at some point in your life, nice work, good for you. I wish you luck. It's not easy, but in the end, hopefully it'll be worth all the hard work, the sweat and tears that you put into it. So let's start by finding what lowercase p, q, n, and x are with this one, and then we'll just plug stuff in from there. So the probability of success is going to be this 1.27%, which you could write. We can move the decimal 2 spots, so think of it like that. 1, 2, you're going to have 0.0127. Let's make a note in color off to the side on this one. This is the same as 1.27%, just in a decimal form. So that's where that number comes from. We're going to have to change decimals to percents and vice versa sometimes with problems in probability. So probability of failure now, that's my lowercase q, that would just be 1 minus this. So that would be the remainder of this. It would be 99.73%, or in other words, 0.9973. I said 9, I meant 8, I'm sorry. So 0.9873, 98.73%. There we go. So where did that come from? This is just 1 minus the 0.0127. Now what is n and what is x? For this question, n is going to be exactly 2. So let's underline that 2. And we're going to say that n equals 2 for this one. And what is x? Man, I am not doing so good here. I meant to say that x equals 2 and n equals 10 because we have 10 people to select. So n is the total number of trials. We're having 10 people, 10 trials, and of those, we're saying exactly 2 are going to be selected. So now from here, let's see what we got. Let's see what that looks like in our probability formula, our binomial probability formula. So p of 2, just going to plug in the numbers right away now. On this one, it would be 10 choose 2. And then your probability of success, that goes here, so 0.0127 to the x power, so to the second power, and then q goes here, so the 0.9873, that to the 10 minus 2 power, the n minus x power. 10 choose 2. If you really wanted to, you could go back to this right here, if you didn't have a calculator, you can use Pascal's triangle. 10 choose 2 is going to be 45 right here. Or you can plug that into a calculator, or you can work it out longhand as well. But this would be 45 any way you swing it. You've got that, and then 0.0127 to the second power. I'm going to leave that like that for now. And then I'm going to leave this decimal as it is for now. This would be to the 8th power. Now at this point I would highly recommend just putting that all at once into a calculator and seeing what you would get. So let's take out a calculator here. My calculator should be able to handle this just fine here. So 45 times 0.0127, that's going to be to the second power, times 0.9873, that's going to be to the 8th power. And so I'll do this all at once here, and I should get this number right here. So I'm going to write down quite a few decimal places to this. I've got 0.006552591. And so what would this be? Let's round this off to the nearest hundredth of a percent. You would move the decimal 2 spots. So let's show that in a different color here. 1, 2, show that right there, and then we're going to say this is approximately, it's actually less than 1/10 of a percent chance of this happening. So 0.6, and if you were to round this off, it would be 0.66. So 0.66%. This is the answer as a decimal. This is an answer rounded off as a percent. This is actually still rounded off, so I'm going to put approximately right here too. Approximately equal to right there, approximately that. And does this make sense? Is this reasonable to say that there's going to be less than 1% of people, or less than 1% of the time where this would happen? Is there a very good chance of picking just one person from a group of 10? I would say definitely not. So exactly 2 people is going to be even lower, way lower than picking 2 out of 10. The chance of picking 1 out of 10 is not going to be 1.27%, but it's not going to be very good. That's more what I should say. But picking 2 people or more than 2 people, oh my gosh, it's going to get crazy. It's going to be really, really hard. So any random 10 people you select, since there's only 1 in about 100 that even has a PhD, to have a PhD in that group of 10 that you picked would be pretty tough to do. It'd be pretty unlikely. So this, in that context, thinking about it like that, I think that really does make sense, that answer. Let's do part B now and part C, and we'll call it good. So none of 10 people selected at random has a PhD. So that would be, none would be x equals 0. So the probability of nothing, nobody, none, nada, what else, nil. I'm out of synonyms for 0. Okay, so 10 choose 0, and then you have still that same percentage, still that same decimal point, 0.0127. This is going to be now to the 0 power. So that's the x power, and then this would be 0.9873 to the 10 minus 0 power. This would be, there's only one way to pick 0 out of a group of 10. This would be, it's going to change, I'll do that in the next step, but it's going to change to the 1st power, and this would be the 10th power. So at that point, I would say just put that into a calculator, see what you get. This and this, you don't even need to do that part, because this is going to be 1. Anything to the 0 power is 1, except for 0 to the 0 power, which is just crazy. And then this 0.9873 to the 10th power, that ends up being what you are about to see here. So I did this already in the calculator. I double checked it to make sure, and it is still rounded off, so I'm going to put approximately equal to what you see here. Okay, and if I move that decimal 2 spots, boom, boom, 1, 2, that would be as a percentage. Sometimes it's easier to think of things in terms of percentages. This would be about 88.00% if I rounded to 2 decimal places, which would be about 88%. And so is that the most likely thing to happen? Because that's definitely more than half. It's almost close to 90% there. Would it make sense that out of a group of 10 people selected at random, that none would have a PhD if there's only a 1.27% chance of having anybody with a PhD? I would say, yeah, I would definitely argue that that would be the most likely thing to happen, that there's probably not anybody with a PhD in the group to begin with, and so this would be the most likely outcome. But part C, now let's say this, at least one person. Oh, one of those at least problems. Initially look very difficult, but then you think about it and then it's one of the easiest problems you can do. So at least one person of 10 selected at random has a PhD. So if we didn't think about it carefully, we might be thinking, oh my gosh, I've got to calculate the probability then of 1 person of 10, 2 of 10, 3 of 10, 4 of 10, 5 of 10, 6, 7, 8, 9 of 10, and then add all those together. That is going to take forever. I don't have that much time. Well, okay, hold on. Didn't we just figure out the probability that none of 10 were selected? Yep. And what are they all supposed to add to? 1 or 100%. And so if we take the probability of none, subtract it from 1, that will be at least one person. That's what's left over. So, woo, yeah, that's nice. So just like before, we've seen this a few times in this chapter. The probability of at least one of certain thing happening is the same as 1 minus the probability of nothing happening. So minus the probability of none in this case. That would become about 1 minus the 0.88 like we saw here. And so that is going to be about 0.12 or 12%. And that's going to be it for this lesson for us. Please look at the examples in your book. There's 4 other good examples. I felt like I could condense the notes here at least down to 2 examples, but 4 more good examples to look at in your book if you need some extra help with those things. Go for it. If you want to go for a PhD, go for it. Just know that it's going to be tough, all right? So you're going to put a lot of work, a lot of effort into it. PhD, do I want to go for one? I don't know. It's a big commitment, but good luck to those of you that want to, and good luck with this lesson, guys. Let me know if you have any questions. Thanks, guys.